So this project began with the question, how can we bring industrial robots into the construction industry? Ron and I saw this as an opportunity to change the ancient process of casting concrete. It's been used since the Bedouins, and it really hasn't changed for thousands of years. So Ron and I thought, what if we can use the precision of industrial robots and the freedom of fabric to create an adjustable mold that could be precisely placed, and we could use the concrete to fill the forms. So you could theoretically design any complex geometry, but using the precision of robots, create in a sense, a brick that could be aggregated and bolted together to create any geometry.
What's really interesting about this pavilion is that no two pieces are the same. And the process that we use means that the robots can create infinite number of unique pieces that will all align perfectly into the entire composition. We took the fabric and we manipulate it with the robots, and we fill it with high-strength concrete and create components that we can then assemble into sculptural objects, or in this case, into the Mars Pavilion.
So the robots we thought we were going to use were about 3 feet tall. We thought we'd be able to get away with small robots that tension fabric, and we pour the concrete and we'll be done. In the end, we realized we needed heavier strength robots with higher payloads. We needed at least robots with 500 pounds of payload so that they could not only take the weight of the concrete, that they could keep the fabric in tension to avoid sagging. So in order to do that, we reached out to ABB Robotics. They were generous enough to loan us 2 IRB 6700 robots. They shipped them to Los Angeles. We were able to use them. So they came in on steel pallets. Each robot with its pallet weighed about 8,000 pounds. So we needed heavy-duty forklifts to get it into our small warehouse. We brought them in, laid them down on the slab, bolted them together, and from then we had to calibrate them. So even though they're perfectly aligned in the digital world, our computer model has them perfectly mirrored, we realize in the physical world the floor that they're sitting on isn't perfectly flat. The way they're bolted onto the pallet isn't perfectly aligned. So we realized we needed to install multi-move, both hardware and software that ABB makes, to calibrate them such that one robot knows where the other one is at all times.
We designed an armature that fits between the 2 robots that we suspend the fabric from.
So our armature is the steel piece that sits in the middle between the robots. And each robot, we attached a spike onto the ends. Those spikes were sharpened down to a fraction of a millimeter. And David, our technician from ABB, calibrated them. So what this let us do is, instead of the robots seeing themselves as 2 6-axis robots, they were both running off of the same CPU, so that they saw themselves as one 12-axis robot. So there was 0 lag between one robot and the other when they were moving. They were acting in perfect harmony. So we were able to not only achieve the precision that was required, but the motion in doing that was perfectly coordinated. So that was one of the breakthroughs that allowed us to do some of the stretching and coordinated efforts that we needed for this project.
As we were going through this process, we had to design end-arm tools for the robots. We came up with a system of clamping the fabric rapidly and securely. We came up with ways of attaching it to the top of the armature and making sure that once we capped the pieces that everything would sit flush. We spent weeks just going through and perfecting the assembly line process of this so that each piece could be replicated with the same level of precision, even though they're all different. We spent a lot of time developing the actual formwork that goes on the industrial robots. And we experimented with all different kinds of fabric. Initially, we did projects that were designed with using really flexible fabric, lycra, which is like spandex, and it meant that every piece of formwork could be the same. You just stretch it into position. But in the end, for this project, we needed something that had greater stiffness to it, that wouldn't sag under the pressure of the concrete. And we used a ballistic nylon that is able to withstand the tensile forces of the robots. And when we sew it into sleeves, and then we even stiffen the ends of the sleeves at the lowest points where they are on the robots so that they don't sag even more. And when we put them on the robots, we set the robots up a couple of inches shorter than where the ultimate size will be, and then we stretch them to their ultimate dimension. And the fabric then is taut. We can fill it with the concrete, and it fills to its full volume without sagging. We used a rapid set product. We used this microfiber, little tiny twisted rebar that goes everywhere within the mix, and it's called helix steel. And we combine that with plasticizers and this high strength concrete, mix it all up, put it into the forms. But inside that form, we also have a 3/16 steel aircraft cable that is tying each leg together all the way up through the top of the piece, so that even in the event that we have a crack in the concrete, that cable is acting as a fail-safe and keeping everything from collapsing.
So we were able to rapidly cast each piece, take it off the robots, and then move the robots to the next piece. And we had gotten this down to clockwork, so it was taking about 75 minutes from the time of casting to taking it off the robots to setting up the next one so that we could move efficiently. In the beginning, we were casting maybe one piece a day, and by the end of the process, we had gotten it down to 8 pieces a day.
In the heat of Palm Springs, about 80 to 90 degrees Fahrenheit, we wind up with pallets of concrete sitting on a lawn and a deck that we're supposed to put this pavilion on unfinished. And we have to start working to finish the deck and erect the pavilion. Before we shipped these pieces to Palm Springs, we never even put 2 pieces together. We didn't have time. We knew it would work, but we couldn't prove it. So the first day we spent working with the carpenters to line up all of the bolt holes, which had to be highly accurate so that the whole piece would go up in exactly the way it was designed. And then we used a router to create a notch in the bottom of the plywood, which accepted a steel plate that we would then bolt our footings onto. Then all of that got screwed down to the deck and covered with this beautiful glossy finished floor.
The first day, we get on site and by the end of the day, we were ready to bolt the first two together, and we thought this is a good opportunity to get started. I have Andrew assemble the first two, and these pieces needed to align perfectly. They needed to align to within a 1/16 of an inch. We go to assemble them, and they're about a foot apart. And I think to myself, either everything is off or I'm going crazy. So I take a step back and I'm getting some air when Andrew notices, wait a minute, this piece was just mislabeled. He rotates it around, and sure enough, they fit perfectly.
After everybody left and the sun was setting, we set the first 8 pieces onto the platform, and it was miraculous.
Compared to a traditional building where you have a floor plan and sections and elevations, all we had in terms of drawings for this project was one puzzle piece looking roadmap. So we saw an opportunity to label every component, because no two are the same. So we labeled the components, and we also labeled the ends of each component, so we know how they fit together. And because of that, we were able to not only rapidly assemble these things, but rapidly communicate to someone who had never seen this before how they're erected, how they fit together. So this gave us the opportunity to move rather quickly through the process of construction.
The second day, we raised the structure up to about 8 feet high and started getting up on scaffolding and going around and using a genie lift to raise the pieces, and everything was looking great. And the third day, we raised up all the pieces and got them together, except that the top 3 pieces were missing each other by about 3 or 4 inches, each one, in different directions. And so we realized that we had to treat this whole structure like you would a bicycle wheel. So if you have a spoke that's out on a bicycle and the wheel is starting to go wobbly, you have to adjust alternate sides of the wheel to get it into line so that the wheel runs straight. That means loosening some, tightening some, but you work back and forth across the whole structure. And in this case, when we got to the top and these pieces didn't meet, we just started working our way around and backed out all of the bolts until the structure started to realign itself. We moved the top pieces in and tightened the bolts all back up again, and we were done.
This entire project, we were not just learning how to build something that's never been built, we were having to teach the people around us how to do that as well. So it was a lesson not just in constructability, but in teaching as well. So how do we impart that knowledge, and how do we make a simple diagram that either a fabricator or a coworker can understand? So this entire project was really, it was a challenge in how do you build something that's never been built before, and how do you do it in a cost-effective and time-efficient way?
Architecture students around the world have taken digital technology and been able to create curvilinear geometry, which is beautiful to design, but extremely difficult to fabricate. What Joey and I have done is been able to find a way to bridge the gap between the digital and the physical. And we believe that this can revolutionize the industry.